The James Webb Space Telescope just shattered our understanding of cosmic history. When astronomers pointed humanity's most powerful eye toward the deepest reaches of space, they expected to find a dark, empty universe slowly awakening from the cosmic dark ages. Instead, they discovered something that challenges everything we thought we knew about how the universe began. In the most distant cosmic depths, over 13 billion light-years away, Webb found massive, mature galaxies blazing with the light of billions of stars. These cosmic giants shouldn't exist. They formed when the universe was barely 400 million years old, just 3% of its current age. It's like finding a towering oak tree in a forest that was planted yesterday. The discovery has astronomers scrambling to rewrite textbooks. For decades, we believed the early universe was a simple place where small clumps of matter slowly grew into larger structures over billions of years. But Webb's infrared vision has revealed a cosmos that was creating massive, complex galaxies at speeds that seem to violate everything we understand about cosmic evolution. Dr. Ivo Labbé, the astronomer who first spotted these ancient giants, couldn't hide his amazement. We looked at the very early universe for the first time and found something so unexpected that it creates problems for science. These aren't just slightly larger galaxies than expected. They're monsters containing nearly as many stars as our own Milky Way, formed in a cosmic instant. The implications ripple through every aspect of cosmology. If galaxies could grow this massive this quickly, it means the universe was capable of organizing matter in ways we never imagined possible. Dark matter, the invisible scaffolding that shapes cosmic structure, must have been clumping together far more efficiently than our models predict. But that's just the beginning of Webb's shocking revelations. The telescope has also discovered supermassive black holes wandering through space without any surrounding galaxy. Cosmic monsters with the mass of 50 million suns drifting alone through the void. These naked black holes challenge our understanding of how such objects form and survive. Even more disturbing, Webb found black holes that appear older than the first stars. Traditional theory says black holes form when massive stars die in explosive supernovas. But Webb detected black holes existing when the universe was too young for stars to have lived and died. Either our timeline of cosmic evolution is completely wrong, or these black holes formed through processes we've never identified. The telescope's discoveries extend beyond just finding unexpected objects. Webb has revealed that the universe itself might be expanding in ways that break the laws of physics. Measurements of cosmic expansion show contradictory results depending on where and how astronomers measure it. As if different regions of space are stretching at different rates, this Hubble tension suggests either our fundamental understanding of cosmic expansion is flawed, or unknown forces are tearing reality apart in ways we can't comprehend. The precision of Webb's measurements has eliminated any possibility that these contradictions result from observational errors. Webb's journey to these discoveries required pushing technology to its absolute limits. Floating 1 million miles from Earth at the L2 Lagrange point, the telescope operates at temperatures just 40 degrees above absolute zero. Its 18 gold-plated mirror segments work together with precision measured in nanometers, creating an instrument capable of detecting the infrared glow of objects that formed when the universe was in its infancy. The infrared radiation Webb collects carries information about cosmic conditions from over 13 billion years ago. Each photon that reaches the telescope's detectors has been traveling through space since before Earth existed, carrying messages from an era when the cosmos operated under rules we're only beginning to understand. These discoveries represent more than just new astronomical findings. They're forcing humanity to confront the possibility that our cosmic origin story is fundamentally incomplete. The universe Webb reveals is stranger, more violent, and more complex than we ever dared imagine. To understand why Webb's discoveries are so shocking, you need to grasp something fundamental about looking into space. Every time we observe distant objects, we're literally looking back in time. Light from the most distant galaxies has been traveling toward us for over 13 billion years, showing us the universe as it existed when it was just a cosmic infant. When Webb peers into the deepest reaches of space, it's not just taking pictures, it's performing cosmic archaeology. The telescope is essentially a time machine that allows us to witness the universe's birth and early development. The farther we look, the further back in time we see, until we approach the very moment when the first stars began to shine. This is why Webb's discoveries are so revolutionary. Astronomers expected to find a young, chaotic universe still forming its first simple structures. Instead, they discovered a cosmos that had already achieved remarkable complexity and organization in what should have been its earliest, most primitive phase. The cosmic dark ages, the period between the Big Bang and the formation of the first stars, was supposed to last several 100 million years. During this time, the universe should have been filled with nothing but hydrogen, helium, and dark matter slowly clumping together under gravity's influence. No stars, no galaxies, no complex chemistry, just the gradual assembly of the cosmic building blocks. But Webb's infrared vision has shattered this timeline. The telescope found massive, mature galaxies shining brightly when the universe was barely 400 million years old. These aren't the small, irregular proto-galaxies that models predicted should exist during this epoch. They're sophisticated spiral and elliptical systems that look remarkably similar to galaxies we see in the nearby universe today. Dr. Erica Nelson, who first identified these universe-breaker galaxies, described the shock of discovery. We were looking for baby galaxies, and instead we found teenagers. The analogy captures the magnitude of the surprise. Imagine expecting to find newborns in a cosmic nursery and discovering fully developed adolescents instead. The speed of this galactic maturation defies our understanding of how cosmic structures form. Galaxy formation requires multiple complex processes working together. Dark matter must clump into halos, gas must fall into these gravitational wells, stars must form from condensing clouds, and stellar feedback must regulate continued growth. Each step takes time, and the whole process should require billions of years. Yet these ancient galaxies accomplished in a few 100 million years what our models say should take several billion. They somehow fast-tracked their development, reaching maturity when the universe itself was still learning how to form stars efficiently. The discovery forces astronomers to confront uncomfortable possibilities about cosmic evolution. Either our models of galaxy formation are fundamentally flawed, or the early universe operated under physical conditions so different from today that familiar processes worked at impossible speeds. Some theories suggest that the first generation of stars was far more massive than anything we see today, monsters containing hundreds of times the mass of our Sun. These stellar giants would have burned through their nuclear fuel in just a few million years before exploding in hypernovas that scattered heavy elements across vast regions of space. This rapid chemical enrichment might have accelerated galaxy formation beyond current predictions. Another possibility involves dark matter behavior in the early universe. Perhaps dark matter particles interacted more strongly during the cosmos's youth, allowing gravitational structures to form much more rapidly than today's physics would permit. These interactions might have provided the additional organizing force needed to build massive galaxies at impossible speeds. Webb's time machine capabilities also revealed the chemical sophistication of these early galaxies. Spectroscopic analysis shows they contain substantial amounts of heavy elements: carbon, oxygen, nitrogen, and even heavier metals like iron. This chemical complexity indicates that multiple generations of stars had already lived and died to create and distribute these elements throughout the galactic medium. The presence of heavy elements so early in cosmic history compressed the entire timeline of stellar evolution into the universe's first few 100 million years. What should have been a gradual process spanning billions of years appears to have happened in cosmic fast-forward. These discoveries represent more than just surprising observations. They're forcing a fundamental reconsideration of how the universe evolved from simplicity to complexity. The cosmic time machine has revealed that our origins story needs dramatic revision. Deep in Webb's most detailed images of the early universe, astronomers began noticing something strange. Scattered throughout the cosmic deep field were tiny crimson dots, objects so faint they appeared as mere pinpricks of red light. But when researchers analyzed these mysterious red dots more carefully, they discovered something that defies explanation. These little red dots don't fit into any known category of cosmic object. They're too bright to be normal galaxies, too compact to be star-forming regions, and too energetic to match anything in our understanding of early universe physics. Each one blazes with the power of billions of stars, yet they're smaller than a typical galaxy and emit most of their light in infrared wavelengths that suggest extreme conditions. Dr. Jorrit Matthey from the Institute of Science and Technology, Austria, led the team that first identified these enigmatic objects. "We have discovered a new population of compact objects in the early universe," he explained, but even he admits they don't know what these objects actually are. The red dots appear in every deep field image Webb has captured, suggesting they were once common throughout the early cosmos. The mystery deepens when astronomers examine the red dot's spectra, the breakdown of their light into component wavelengths that reveals their physical properties. These objects show emission lines that indicate incredibly hot, dense gas moving at tremendous speeds. The spectral signatures suggest matter being heated to millions of degrees and accelerated to a significant fraction of light speed. Such extreme conditions typically occur near supermassive black holes, where gravitational forces compress and superheat surrounding matter into brilliant accretion disks. But the red dots are far too small and compact to be typical galaxies hosting supermassive black holes. They might represent a completely unknown phase of black hole growth that occurred during the universe's youth. One possibility is that these red dots are direct collapse black holes, massive objects that form through gravitational collapse of enormous gas clouds without ever going through a stellar phase. In the early universe's dense environment, entire regions of space might have collapsed directly into black holes, skipping the normal process of star formation and stellar death. Another theory suggests the red dots might be the universe's first quasars, supermassive black holes feeding so voraciously that their accretion disks outshine the entire galaxies surrounding them. These feeding frenzies would create exactly the kind of compact, ultra-bright objects Webb is detecting in the cosmic deep. But the red dots challenge even these explanations. Some appear to vary in brightness over relatively short timescales, suggesting dynamic processes operating much faster than normal galactic evolution. If these objects are changing significantly over periods of months or years in their own time frame, they must be undergoing incredibly violent and rapid transformations. The spatial distribution of red dots across Webb's images also poses puzzles. Rather than clustering in regions where early galaxy formation was expected, they appear randomly scattered throughout space. This random distribution suggests they might represent a fundamental property of the early universe rather than rare, isolated phenomena. Perhaps most intriguingly, many red dots appear to exist in cosmic voids, regions of space with relatively little matter. Finding such energetic objects in these sparse environments challenges our understanding of how massive structures could form in regions with insufficient raw material for typical galaxy assembly. The abundance of red dots forces astronomers to reconsider how common extreme objects were in the early universe. If every deep field image contains dozens of these mysterious sources, the early cosmos might have been far more violent and energetic than previously imagined. Instead of a gradual awakening from the cosmic dark ages, the universe might have experienced a period of widespread, catastrophic events. Some researchers speculate that red dots might be connected to the rapid galaxy formation Webb has observed elsewhere in the early universe. Perhaps these compact, energetic objects represent the seeds around which massive galaxies quickly assembled, providing the energy and organizational structure needed for accelerated cosmic evolution. The red dot mystery represents one of Webb's most perplexing discoveries because it reveals an entirely unexpected population of cosmic objects. These aren't just unusual examples of known phenomena. They appear to be something completely new that existed during the universe's youth but has no analog in the modern cosmos. Understanding the red dots might be crucial for solving the broader puzzle of how the early universe achieved such rapid complexity. Whatever these objects are, they were clearly playing an important role in cosmic evolution during an epoch when the universe was supposedly simple and underdeveloped. In the deepest reaches of space, Webb discovered something that breaks every rule of black hole formation. Floating in the cosmic void, 13 billion light-years from Earth, are supermassive black holes containing millions of solar masses, but they exist at a time when such monsters shouldn't be possible. These ancient black holes pose what astronomers call the supermassive black hole timing problem. Traditional theory requires black holes to grow from stellar seeds. When massive stars die in supernova explosions, they leave behind black holes typically 3 to 20 times the mass of our Sun. These stellar mass black holes then gradually accumulate matter over billions of years, slowly growing into the supermassive giants we see at galaxy centers today. But Webb found fully formed supermassive black holes already blazing in quasar activity when the universe was just 400 to 600 million years old. There simply wasn't enough time for stellar mass black holes to grow this large through normal feeding processes. Even if these primordial black holes fed continuously at the maximum theoretical rate, called the Eddington limit, they couldn't have reached such enormous masses so quickly. Dr. Rebecca Larson from the University of Texas discovered some of the most extreme examples. We're seeing supermassive black holes when the universe was only 3% of its current age, she explained. It's like finding adult elephants in a world where life just learned to walk on land. The comparison captures the temporal impossibility. These cosmic giants appeared before the universe had time to create them through known processes. The discovery forces astronomers to consider radical alternatives to standard black hole formation. One possibility involves direct collapse black holes that formed without any stellar progenitor. In the dense, chaotic conditions of the early universe, enormous gas clouds might have collapsed directly into black holes with initial masses thousands of times greater than typical stellar remnants. This direct collapse scenario requires extremely specific conditions. The gas clouds would need to remain incredibly hot to avoid fragmenting into individual stars during collapse. Intense radiation from the universe's first stars might have provided the heating necessary to keep these clouds intact as they collapsed into massive black holes. Another theory suggests that the universe's first generation of stars were far more massive than anything we see today. These population 3 stars might have contained hundreds or even thousands of solar masses, burning through their nuclear fuel in just a few million years before collapsing into intermediate mass black holes. These larger seed black holes could then grow to supermassive scales more quickly than stellar mass remnants. Webb's observations reveal additional mysteries about these ancient black holes. Many appear to be feeding at rates that exceed theoretical limits, consuming matter faster than physics should allow. When black holes feed too rapidly, the intense radiation from superheated matter should blow away additional material, creating a self-regulating mechanism that prevents runaway growth. Yet some of Webb's black holes show signs of super-Eddington accretion, feeding frenzies that violate this fundamental limit. These cosmic monsters are somehow stabilizing their feeding processes despite radiation pressures that should shut down further growth. Either they've found ways to circumvent physical limits, or the early universe provided feeding conditions unlike anything that exists today. The black holes Webb discovered also challenge our understanding of galaxy formation. In the modern universe, supermassive black holes and their host galaxies grow together in a carefully balanced relationship. The black hole's gravitational influence shapes the galaxy's structure, while stellar feedback regulates the black hole's growth. But many of Webb's ancient black holes appear to exist without substantial galactic hosts. These naked black holes shine brightly in X-ray and infrared light, indicating active feeding but show little evidence of surrounding stellar populations. They represent cosmic orphans, massive objects that somehow formed and survived without the galactic nurseries that should have created them. Perhaps most disturbing is what these impossible black holes suggest about cosmic violence in the early universe. If supermassive black holes could form through direct collapse or super rapid growth, the universe's first billion years might have been far more chaotic and extreme than our models predict. These discoveries are forcing a complete reconsideration of how cosmic structure emerged from primordial simplicity. The universe Webb reveals operated under conditions so extreme that familiar physics broke down, allowing massive objects to form through processes we're only beginning to understand. The universe has a fundamental problem, and Webb just made it worse. For over a decade, astronomers have been measuring how fast the universe is expanding, but they keep getting 2 different answers depending on how they make the measurement. This contradiction, known as the Hubble tension, suggests that either our understanding of cosmic expansion is completely wrong, or unknown physics is operating on the largest scales imaginable. The crisis began when precision measurements of the cosmic microwave background, the afterglow of the Big Bang itself, predicted one expansion rate, while direct observations of distant stars gave a significantly different rate. The discrepancy was troubling but small enough that many hoped better measurements would resolve the conflict. Instead, Webb's unprecedented precision has made the problem worse. The telescope's infrared capabilities allow it to observe Cepheid variable stars, cosmic lighthouses that pulsate with predictable brightness patterns at much greater distances than ever before. These stellar beacons serve as standard candles that astronomers use to measure cosmic distances and calculate expansion rates. Dr. Adam Rees, the Nobel laureate who discovered cosmic acceleration, led Webb's investigation of the Hubble tension. His team observed over 1,000 Cepheid stars across multiple galaxies, extending measurements out to 130 million light-years. The results were unambiguous. Webb confirmed the higher expansion rate measured by direct observations, deepening the conflict with predictions from the early universe. The tension isn't a small disagreement between measurements. It represents a fundamental crisis in cosmology. The two methods disagree by about 8%, which might sound minor, but in terms of cosmic expansion, this difference is enormous. It's like two surveyors measuring the same mountain and getting heights that differ by hundreds of feet despite using calibrated instruments. This discrepancy has profound implications for our understanding of the universe's composition and fate. If the expansion rate measured by Webb is correct, it means the universe is about 12.5 billion years old. But if the cosmic microwave background predictions are right, the universe is closer to 13.8 billion years old. The difference of over 1 billion years completely changes our understanding of cosmic history. The crisis deepens when we consider what might cause such a fundamental disagreement. One possibility is that dark energy, the mysterious force driving cosmic acceleration, isn't constant but changes over time or varies in strength across different regions of space. If dark energy has been growing stronger over cosmic history, it could explain why local expansion measurements exceed early universe predictions. Another disturbing possibility involves dark matter, the invisible scaffolding that shapes cosmic structure. Perhaps dark matter interactions were different in the early universe, affecting how sound waves propagated through the primordial plasma and altering the cosmic microwave background patterns we use to calculate expansion rates. The most radical explanation suggests that our fundamental understanding of gravity might be incomplete. Einstein's general relativity has passed every experimental test, but the Hubble tension could indicate that gravity behaves differently on cosmic scales or during certain phases of universal expansion. Webb's observations have also revealed unexpected structure in the cosmic distance ladder, the series of measurements astronomers use to gauge distances across the universe. Some of the galaxies Webb observed show evidence of unusual stellar populations or environmental effects that could systematically bias distance measurements in ways we don't fully understand. The telescope's infrared sensitivity has uncovered dust and gas around Cepheid stars that was invisible to previous observations. This material could affect how we interpret the stars' brightness variations, potentially introducing systematic errors that propagate through the entire cosmic distance scale. But perhaps the most unsettling aspect of the Hubble tension is what it suggests about the limits of human knowledge. Despite decades of increasingly precise measurements using multiple independent techniques, we cannot determine one of the most fundamental properties of our universe: how fast it's expanding. The crisis forces astronomers to confront the possibility that our cosmological model, successful as it has been in explaining observations, might be missing crucial physics. The universe. Webb reveals operates according to rules we haven't fully grasped, expanding in ways that challenge our most basic assumptions about cosmic evolution. Whether the solution involves new physics, unknown systematic errors, or fundamental flaws in our cosmological model, the Hubble tension represents one of the most significant challenges to modern astronomy. The universe is expanding, but we can't agree on how fast, a humbling reminder of how much we still don't understand about the cosmos we inhabit. Webb didn't just find unexpected galaxies in the early universe. It revolutionized our understanding of when cosmic dawn actually began. The telescope's infrared vision has pushed back the frontier of first light, revealing that stars began shining hundreds of millions of years earlier than we thought possible, fundamentally altering the timeline of cosmic evolution. Before Webb, astronomers believed the universe experienced a prolonged dark age lasting 400 to 500 million years after the Big Bang. During this epoch, the cosmos should have been filled with neutral hydrogen gas slowly cooling and clumping under gravity's influence, but no stars yet existed to illuminate the cosmic darkness. The first stellar ignition was expected around 400 million years after the Big Bang, marking humanity's observational horizon. But Webb shattered this timeline by detecting mature stellar populations when the universe was just 300 to 350 million years old. These aren't the simple, metal-poor stars that theories predicted should exist during cosmic dawn. They're sophisticated stellar systems showing evidence of multiple generations of star formation and chemical enrichment that should have required far more time to develop. Dr. Brant Robertson from UC Santa Cruz led one of the key studies revealing this cosmic acceleration. "We're seeing evidence that star formation began much earlier than we expected," he explained. "The universe was making stars when we thought it should still be figuring out how to make them." This discovery compresses the entire timeline of early cosmic evolution into a much shorter window. The implications extend far beyond just pushing back the date of first light. Early star formation requires specific physical conditions, regions of space where hydrogen gas can cool and condense efficiently while avoiding disruption from turbulence or heating sources. Webb's observations suggest these conditions existed throughout the early universe far more readily than models predicted. The telescope's discoveries also reveal that early stars were incredibly efficient at producing heavy elements. Spectroscopic analysis of ancient galaxies shows surprisingly high concentrations of carbon, oxygen, and nitrogen, elements that can only be forged in stellar cores and distributed through supernova explosions. Finding such chemical sophistication so early in cosmic history means stellar nucleosynthesis operated at accelerated rates. This rapid chemical evolution had profound consequences for subsequent cosmic development. Heavy elements are crucial for planet formation, dust grain production, and the complex chemistry that enables efficient star formation in later epochs. By enriching the universe with metals much earlier than expected, the first stellar generations created conditions that accelerated all subsequent cosmic evolution. Webb's observations of cosmic reionization, the process by which early stars ionized the neutral hydrogen-filling space, also reveal surprising patterns. Instead of a gradual, uniform process extending over hundreds of millions of years, reionization appears to have been rapid and patchy, with some regions becoming ionized much earlier than others. The telescope detected ionization bubbles around early galaxies where stellar radiation had cleared away neutral hydrogen, creating transparent regions in an otherwise opaque universe. These bubbles appear larger and more numerous than simulations predicted, suggesting early stars were more luminous and numerous than theoretical models allowed. Perhaps most significantly, Webb found evidence that supermassive black holes were already influencing cosmic evolution during this earliest epoch. The telescope detected quasar activity, indicating actively feeding black holes in some of the universe's first galaxies. These ancient monsters were already regulating star formation and galactic development when the cosmos was supposedly in its most primitive phase. The early appearance of both sophisticated stellar populations and supermassive black holes suggests that cosmic structure formation operated under fundamentally different conditions than we understand. The dense, uniform early universe might have supported formation mechanisms that don't exist in today's cosmos, allowing rapid development of complex structures. Webb's revolution in understanding cosmic dawn forces astronomers to reconsider the entire narrative of how the universe evolved from simplicity to complexity. Rather than a gradual awakening from the Dark Ages, cosmic evolution appears to have been front-loaded, with crucial developments occurring much earlier and more rapidly than previously imagined. These discoveries transform our understanding of cosmic habitability as well. If heavy elements and complex chemistry became available hundreds of millions of years earlier than expected, potentially habitable worlds could have formed much sooner in cosmic history. The universe might have been capable of supporting complex chemistry and potentially life far earlier than we ever considered possible. Webb uncovered galaxies in the early universe that shouldn't be able to exist according to our understanding of cosmic structure formation. These massive stellar systems achieved sizes and masses that required billions of years to develop, yet they formed when the universe was barely out of its infancy. The discovery has forced astronomers to confront the possibility that galaxy formation operates through mechanisms we've never identified. The problem centers on what astronomers call the assembly time crisis. Computer simulations of cosmic evolution show how dark matter halos grow through gravitational collapse, gradually accumulating enough material to host galaxy formation. These models predict that massive galaxies should only appear after dark matter has had sufficient time to build the gravitational scaffolding needed to support them. But Webb found massive galaxies comparable to our Milky Way already fully formed just 400 to 500 million years after the Big Bang. These cosmic giants contain stellar masses of 10 to 100 billion solar masses, amounts that should have taken several billion years to accumulate through normal star formation processes. Dr. Ivo Labe from Swinburne University of Technology described the discovery's impact. These galaxies are way more massive than anyone expected. It's like finding a toddler who weighs 200 pounds. It challenges everything we understand about normal development. The analogy captures how fundamentally these observations violate theoretical expectations. The stellar populations within these early massive galaxies present additional puzzles. Spectroscopic analysis reveals surprisingly mature stellar chemistry, with evidence of multiple generations of star formation and death. This chemical sophistication indicates that numerous cycles of stellar evolution had already occurred, compressing billions of years of galactic development into the universe's first few hundred million years. Traditional galaxy formation requires a carefully orchestrated sequence of events. Dark matter must first clump into gravitational wells, then hydrogen and helium gas must fall into these wells and cool efficiently. Star formation must begin and proceed at sustainable rates, and stellar feedback must regulate continued growth. Each step has physical limitations that constrain how quickly the process can proceed. Yet the massive early galaxies Webb discovered appear to have bypassed these constraints entirely. They formed stars at rates exceeding 100 solar masses per year, compared to our Milky Way's current rate of about 2 solar masses annually. Such extreme star formation should trigger feedback processes that shut down further stellar birth. Yet these galaxies sustain their frenzied pace long enough to build enormous stellar masses. The efficiency of early star formation also challenges our understanding of cosmic chemistry. The first stars in the universe should have been composed almost entirely of hydrogen and helium, with virtually no heavy elements. But Webb's early massive galaxies show evidence of substantial metal enrichment, indicating that previous stellar generations had already lived, died, and scattered their processed elements throughout the galactic medium. This rapid chemical evolution required the universe's first stars to be fundamentally different from anything we observe today. They likely included population 3 superstars containing hundreds of solar masses that burned through their nuclear fuel in just a few million years, before exploding in hypernovas that could enrich entire galactic regions with heavy elements. Another possibility involves primordial black holes that formed directly from gravitational collapse in the early universe's dense conditions. These massive objects could have served as seeds around which galaxies rapidly assembled, providing both the gravitational anchors and energy sources needed for accelerated development. Webb's discoveries also reveal that early massive galaxies existed in cosmic environments very different from today. The early universe was denser, hotter, and more turbulent, with matter distributed more uniformly than in the current epoch. These conditions might have enabled formation mechanisms that don't operate in the modern cosmos. The implications extend beyond just galaxy formation to our understanding of cosmic structure on the largest scales. If massive galaxies could form so rapidly in the early universe, it suggests that dark matter interactions were more efficient than current models predict, or that additional physics beyond standard cosmology influence structure formation. These discoveries force astronomers to reconsider fundamental assumptions about how cosmic complexity emerges from primordial simplicity. The universe Webb reveals was capable of organizing matter into sophisticated structures far more rapidly than our theories allow, operating under conditions so extreme that familiar physics couldn't constrain the pace of cosmic evolution. Webb discovered something that shouldn't exist in the early universe: fully mature quasars blazing with the power of trillions of stars when the cosmos was less than 700 million years old. These cosmic lighthouses are powered by supermassive black holes, feeding so voraciously that they outshine entire galaxies, but their existence at such early times breaks every model of black hole growth that astronomers have developed. Quasars represent the most extreme feeding events in the universe. They occur when supermassive black holes at galaxy centers consume matter so rapidly that the infalling material forms brilliant accretion disks heated to millions of degrees. The intense radiation from these feeding frenzies can be detected across billions of light years, making quasars among the most luminous objects in the cosmos. The problem is timing. Quasars require supermassive black holes containing millions or billions of solar masses, but these monsters shouldn't exist in the early universe. Even if black holes began forming immediately after the Big Bang and fed continuously at maximum theoretical rates, they couldn't have grown large enough to power the ancient quasars Webb discovered. Dr. Xiaohui Fan from the University of Arizona led the team that identified some of the most distant quasars ever found. We're seeing quasars powered by billion solar mass black holes when the universe was only 5% of its current age, he explained. It's like finding a full-grown adult in a nursery of newborns. The timing problem is so severe that it challenges fundamental assumptions about cosmic evolution. The ancient quasars Webb discovered don't just exist earlier than expected. They're feeding at rates that seem to violate physics. Observations reveal black holes consuming matter at 40 times the Eddington limit, the theoretical maximum rate at which objects can accrete material without the radiation pressure blowing away their food supply. This super Eddington accretion suggests either that our understanding of black hole physics is incomplete, or that conditions in the early universe were so extreme that normal physical limitations didn't apply. The ancient cosmos might have provided feeding environments unlike anything that exists today, allowing black holes to grow through mechanisms we've never observed. Webb's spectroscopic analysis of these impossible quasars reveals additional mysteries. The light signatures show evidence of mature galactic environments with substantial heavy element abundances, indicating that entire stellar ecosystems had already formed and evolved around these feeding black holes. This galactic maturity should have required billions of years to develop. The quasars also appear to be influencing their cosmic neighborhoods in ways that accelerate galactic evolution. The intense radiation and particle winds from actively feeding black holes can trigger star formation in surrounding gas clouds while simultaneously heating material to prevent further accretion. This delicate balance between destruction and creation might explain how galaxies achieve such rapid maturity in the early universe. Perhaps most disturbing is what these discoveries suggest about the prevalence of supermassive black holes in cosmic youth. If Webb can detect quasars this early in cosmic history, it implies that massive black holes were common throughout the universe when it was supposedly in its most primitive phase. The cosmos might have been seeded with these monsters from its earliest moments. Some theories propose that the ancient quasars are powered by primordial black holes that formed directly from the collapse of massive gas clouds in the first few 100 million years after the Big Bang. These direct collapse black holes could have started with masses thousands of times greater than typical stellar remnants, giving them the head start needed to reach quasar powering sizes. Another possibility involves exotic physics operating under the extreme conditions of the early universe. When matter densities were much higher than today, gravitational effects might have been amplified in ways that allowed rapid black hole growth through processes that don't exist in the modern cosmos. Webb's quasar discoveries also reveal something unexpected about cosmic reionization, the process by which early radiation sources ionized the neutral hydrogen-filling space. The ancient quasars appear to be major contributors to this cosmic transformation, creating bubbles of ionized space much larger than expected from their luminosity alone. The implications extend to our understanding of galaxy formation itself. If supermassive black holes were common in the early universe, they would have influenced how galaxies assembled and evolved from the very beginning. Rather than being consequences of galactic evolution, these massive objects might have been the driving forces that shaped cosmic structure formation. These impossible quasars represent one of Webb's most fundamental challenges to cosmology, revealing that the early universe operated under conditions so extreme that our most basic assumptions about black hole growth and galactic evolution require complete revision. Webb discovered something disturbing about dark matter in the early universe. it was behaving in ways that contradict our most fundamental assumptions about this mysterious substance. Observations of ancient galaxy clusters reveal dark matter distributions that don't match theoretical predictions, suggesting either our understanding of dark matter is incomplete or unknown physics was operating during cosmic youth. Dark matter makes up about 85% of all matter in the universe, yet it remains invisible to direct observation. We know it exists because of its gravitational effects. Dark matter's invisible scaffolding shapes how normal matter clumps together to form galaxies and larger cosmic structures. Computer simulations of cosmic evolution depend critically on understanding how dark matter behaves under different conditions. But Webb's observations of early galaxy formation reveal dark matter acting in unexpected ways. The telescope found massive galaxies that formed too quickly given standard dark matter physics, and galaxy clusters with dark matter distributions that don't match what simulations predict should exist during the universe's youth. Dr. Priyamvada Natarajan from Yale University led studies revealing these dark matter anomalies. The early universe shows evidence of dark matter clustering more efficiently than our models allow, she explained. Either dark matter has properties we don't understand, or additional physics was operating that we haven't identified. The anomalies appear most prominently in Webb's observations of gravitational lensing, the bending of light by massive objects that reveals dark matter distributions. When astronomers map how dark matter is distributed in early galaxy clusters, they find concentrations that are too dense and too well organized for the universe's age. Standard cosmology predicts that dark matter should clump together gradually through gravitational collapse, with small structures merging to form larger ones over billions of years. This hierarchical assembly should prevent the formation of very massive dark matter halos in the early universe, simply because there hasn't been enough time for sufficient merging. Yet Webb detected galaxy clusters with dark matter halos massive enough to support entire groups of galaxies when the universe was less than 2 billion years old. These structures should have required much longer assembly times, suggesting that dark matter was organizing itself more rapidly than current physics allows. The telescope also revealed unexpected substructure within early dark matter halos. Instead of the smooth distributions predicted by simulations, Webb found dark matter clumps and voids that indicate complex internal dynamics. These features suggest that dark matter interactions were more complicated during the universe's youth than standard models assume. One possibility is that dark matter underwent phase transitions during the early universe's cooling, changing its properties in ways that affected how it clustered and interacted. Just as water can exist as ice, liquid, or vapor depending on temperature, dark matter might have different behavioral phases that operated under the extreme conditions of cosmic youth. Another theory suggests that dark matter particles can interact with each other through forces beyond simple gravitational attraction. These self-interacting dark matter models could explain why early dark matter halos achieved such high densities and organized structures. The particles were directly influencing each other's behavior rather than only responding to gravity. Webb's observations also hint at connections between dark matter anomalies and the rapid galaxy formation the telescope has observed throughout the early universe. If dark matter was clustering more efficiently than expected, it could have provided the enhanced gravitational wells needed for accelerated star formation and galactic assembly. The dark matter mystery extends to cosmic structure on the largest scales. Webb surveys reveal that the cosmic web, the network of filaments and voids that organizes matter throughout space, was more developed during the universe's youth than simulations predict. This advanced organization suggests that dark matter was shaping cosmic structure through mechanisms we haven't identified. Perhaps most concerning is what these anomalies suggest about our broader understanding of cosmic evolution. Dark matter is the foundation of modern cosmology. Our entire picture of how the universe developed depends on assumptions about dark matter's properties and behavior. If those assumptions are wrong, it could invalidate much of our understanding about cosmic structure formation. The Webb observations don't definitively prove that dark matter has exotic properties, but they reveal phenomena that can't be explained by standard dark matter models. Whether the solution involves new physics, previously unknown particle interactions, or fundamental revisions to cosmological theory, these discoveries challenge one of the most basic components of our cosmic worldview. Understanding dark matter's true nature has become even more crucial as Webb continues revealing unexpected phenomena throughout the early universe. The telescope's observations suggest that the cosmos operated under conditions so extreme that even dark matter, the universe's primary structural component, behaved in ways we're only beginning to comprehend. Webb peered into the largest structures in the universe and discovered something unprecedented. The cosmic web was already fully formed when the universe was supposed to still be building its first simple structures. This vast network of filaments and voids that organizes matter on the grandest scales had achieved a level of complexity and organization that shouldn't have been possible given the cosmos's young age. The cosmic web represents the ultimate expression of cosmic structure, a three-dimensional scaffolding of dark matter filaments stretching across billions of light years, connecting galaxy clusters and defining the architecture of space itself. This web grows through gravitational collapse over cosmic time, with matter flowing along filaments toward nodes where galaxy clusters eventually form. Traditional cosmology predicts that the cosmic web should develop gradually, starting from tiny quantum fluctuations in the early universe that slowly grow into larger structures through gravitational amplification. This process should take billions of years, with the largest structures forming relatively recently in cosmic history. But Webb's deep surveys revealed cosmic web features that were remarkably well developed when the universe was less than 2 billion years old. The telescope detected filamentary structures connecting distant galaxy clusters across hundreds of millions of light years, displaying an organizational complexity that simulations suggest shouldn't emerge until much later in cosmic evolution. Dr. Benedetta Volcani from the Italian National Institute for Astrophysics led studies mapping these ancient large-scale structures. We're seeing cosmic web features that look surprisingly modern, appearing much earlier than our models predict, she explained. The universe achieved large-scale organization faster than we thought possible. The implications extend beyond just timing to fundamental questions about cosmic structure formation. If the cosmic web was well developed early in universal history, it suggests that gravitational collapse operated more efficiently than standard models allow, or that additional physics accelerated the growth of cosmic structure. Webb's observations also revealed unexpected activity within early cosmic web filaments. Instead of the relatively quiet matter flows predicted by simulations, the telescope detected evidence of vigorous star formation occurring within the filaments themselves. Gas streaming along these cosmic highways was apparently dense enough to trigger stellar birth, far from traditional galactic environments. This distributed star formation challenges our understanding of how galaxies assemble. If stars were forming throughout cosmic web filaments rather than just within dark matter halos, it could explain how early galaxies achieved such large stellar masses so rapidly. The cosmic web wasn't just passively funneling matter toward galaxy formation sites, it was actively participating in stellar production. The telescope discovered cosmic web nodes, the intersections where multiple filaments meet that were already hosting massive galaxy clusters in the early universe. These protoclusters contain dozens of galaxies in close proximity, indicating that the cosmic web was efficiently directing matter flows toward cluster formation sites much earlier than expected. Webb's infrared sensitivity revealed warm gas threading throughout early cosmic web filaments, gas that was previously invisible to optical telescopes. This material appears to be heated by shock waves as it flows along filaments and collides at intersection points, creating a dynamic environment of cosmic fluid dynamics operating on the largest possible scales. The discovery of well-developed cosmic web structure in the early universe also affects our understanding of galaxy evolution. Galaxies embedded within this mature web would have experienced enhanced matter, infall, and gravitational interactions that could accelerate their growth and trigger rapid star formation episodes. Perhaps most significantly, Webb found evidence that the cosmic web was influencing the formation and feeding of supermassive black holes. Many of the ancient quasars the telescope discovered appear to be located at cosmic web nodes, suggesting that large-scale structure was channeling matter toward these feeding monsters and enabling their rapid growth. The mature cosmic web Webb observed also reveals something disturbing about dark energy, the mysterious force driving cosmic expansion. If large-scale structures were more developed in the early universe than expected, it might indicate that dark energy's effects were different during cosmic youth, allowing enhanced structure formation before accelerated expansion took over. These discoveries suggest that the universe's transition from smooth initial conditions to complex large-scale structure happened much more rapidly than cosmologists believe possible. The cosmic web represents the universe's attempt to organize itself on the grandest scales, and Webb has revealed that this organization succeeded far earlier and more completely than our models predict. Understanding how the cosmic web achieved such early maturity is crucial for comprehending cosmic evolution itself, as this vast structure provides the framework within which all smaller scale phenomena, from galaxy formation to star birth, ultimately occur. Webb discovered evidence of stellar explosions that occurred when the universe was supposedly too young to produce them. The telescope detected the chemical signatures of supernovas and stellar nucleosynthesis in galaxies that formed just 300 to 400 million years after the Big Bang. But these cosmic catastrophes require multiple generations of stellar evolution that shouldn't have had time to occur. Supernovas represent the violent deaths of massive stars, events so energetic they can outshine entire galaxies for weeks or months. But more importantly, these stellar explosions are cosmic forges that create and distribute heavy elements throughout space. When massive stars exhaust their nuclear fuel, they collapse and explode, scattering carbon, oxygen, silicon, iron, and dozens of other elements that were forged in their cores during millions of years of nuclear burning. The problem Webb uncovered involves cosmic timing. Creating heavy elements through stellar nucleosynthesis requires stars to live complete life cycles, forming from gas clouds, burning hydrogen and helium in their cores for millions of years, and finally dying in explosive supernovas. Even the most massive stars need at least 3 to 4 million years to complete this cycle, and typical stellar lifetimes extend much longer. But Webb found substantial heavy element abundances in galaxies that existed when the universe was barely 300 million years old. This means stellar formation, evolution, and death cycles had already completed multiple times during the cosmos's infancy, a pace of stellar evolution that seems impossible given known stellar physics. Dr. Emma Curtis Lake from the University of Hertfordshire led spectroscopic studies revealing this chemical puzzle. We're seeing carbon and oxygen signatures in galaxies that should be composed almost entirely of hydrogen and helium, she explained. These heavy elements require stellar processing that should take much longer than the universe's age at that time. The discovery forces astronomers to reconsider fundamental assumptions about early stellar evolution. One possibility involves population 3 stars, the universe's first generation of stellar objects that form from pristine hydrogen and helium gas. These primordial stars might have been fundamentally different from anything we observe today. Theoretical models suggest population 3 stars could have been true monsters containing 100 to 1,000 times the mass of our Sun. These stellar giants would have burned through their nuclear fuel at extraordinary rates, completing their entire life cycles in just 2 to 3 million years before exploding in hypernovas. These hypernova explosions would have been cosmic game changers, instantly enriching vast regions of space with heavy elements and triggering shockwaves that could stimulate rapid star formation in surrounding gas clouds. A single hypernova might have provided the chemical seeds for entire galactic regions, accelerating subsequent stellar evolution beyond normal rates. Webb's observations also revealed evidence of pair instability supernovas, theoretical explosions that could only occur in the most massive primordial stars. These catastrophic events completely destroy their parent stars, leaving no stellar remnant behind but scattering enormous quantities of heavy elements across cosmic distances. The telescope detected unusual abundance patterns in early galaxies that match theoretical predictions for pair instability nucleosynthesis. These chemical signatures suggest that some of the universe's first stars underwent explosive deaths, so violent they have no analogs in the modern cosmos, creating heavy element distributions unlike anything produced by contemporary stellar evolution. But even accounting for hypermassive primordial stars, the rapid chemical evolution Webb observed pushes stellar physics to its limits. The telescope found galaxies with metallicity levels indicating that not just one, but multiple generations of stars had already lived and died, creating a chemical complexity that should have required hundreds of millions of years to develop. This accelerated stellar evolution might have been enabled by the unique conditions of the early universe. When cosmic matter density was much higher than today, star formation could have proceeded more efficiently, with gravitational collapse happening faster and stellar birth rates exceeding anything observed in modern galaxies. The early universe's higher density might also have affected stellar structure itself, allowing stars to achieve larger masses and burn more efficiently than modern stellar physics predicts. Under these extreme conditions, normal stellar evolution timescales could have been compressed dramatically. Webb's discovery of early stellar explosions also explains how the rapid galaxy formation the telescope observed throughout the early universe was possible. The heavy elements created by primordial supernovas were essential for efficient star formation, dust grain production, and the cooling mechanisms that allowed subsequent stellar generations to form more readily. These stellar explosions represent more than just accelerated evolution. They reveal that the early universe operated under conditions so extreme that familiar stellar physics was pushed beyond its normal limits, creating cosmic violence that has no equivalent in today's cosmos. To understand how Webb made these universe-shattering discoveries, you need to grasp the extraordinary engineering that allows the telescope to peer deeper into space and time than any instrument ever built. Webb didn't just incrementally improve on previous telescopes, it represents a quantum leap in our ability to observe the cosmos that has fundamentally transformed what's possible in astronomy. The secret lies in Webb's unprecedented infrared sensitivity. While Hubble primarily observes visible light, the same wavelengths human eyes can see, Webb operates in the infrared spectrum, detecting heat radiation that carries information invisible to other telescopes. This infrared vision is crucial for studying the early universe because cosmic expansion stretches light from distant objects into longer, redder wavelengths. Light from the most distant galaxies has been traveling toward us for over 13 billion years, during which time the universe's expansion has stretched these ancient photons from their original visible wavelengths into the infrared. Objects that would appear bright blue when they formed now glow deep red by the time their light reaches Earth. Only an infrared telescope can capture these ancient signals. Webb's primary mirror spans 6.5 meters across, nearly 3 times larger than Hubble's. But the mirror's size alone doesn't explain the telescope's revolutionary capabilities. The mirror consists of 18 hexagonal segments, each coated with a microscopic layer of gold that reflects infrared light with extraordinary efficiency. These segments must align with nanometer precision to function as a single, perfect mirror. The engineering challenge of achieving this precision in space is staggering. Each mirror segment can be adjusted independently using tiny actuators that can move the surfaces by distances smaller than a virus. The entire mirror assembly must maintain its shape while operating at temperatures just 40 degrees above absolute zero in the vacuum of space, while experiencing the gravitational environment of the L2 Lagrange point. Webb's location at L2, about 1 million miles from Earth, provides the stable, cold environment essential for infrared observations. At this gravitational balance point between Earth and Sun, the telescope can maintain a fixed position relative to Earth, while its massive sunshield blocks heat and light from both the Sun and Earth. This allows Webb's instruments to cool to the extreme temperatures needed to detect faint infrared signals. The sunshield itself represents a marvel of engineering. 5 layers of specialized material, each as thin as human hair, stretched across an area the size of a tennis court. This thermal barrier creates a temperature difference of over 600 degrees Fahrenheit between the hot, sun-facing side and the cold, space-facing side where the instruments operate. Webb's infrared detectors push the boundaries of what's physically possible. These sensors can register individual photons that have traveled billions of miles through space, converting infrared radiation into electrical signals with extraordinary precision. The detectors must operate at temperatures just 7 degrees above absolute zero to prevent their own thermal noise from overwhelming the faint signals they're designed to measure. The telescope's spectrographs, instruments that split light into component wavelengths, can analyze the chemical composition of objects across cosmic distances. When Webb observes a distant galaxy, it's essentially performing a chemical analysis of matter that existed when the universe was in its infancy, revealing the elemental composition and physical conditions of cosmic environments from over 13 billion years ago. Data processing presents its own technological challenges. Webb generates enormous amounts of information that must be transmitted across 1 million miles of space, then analyzed using sophisticated algorithms that can distinguish genuine cosmic signals from instrumental noise and systematic effects. The telescope's discoveries require not just extraordinary hardware, but computational techniques that push the limits of data analysis. The precision required for Webb's observations borders on the impossible. To detect the faint infrared glow of early galaxies, the telescope must measure changes in light intensity equivalent to detecting a candle flame on the moon, while maintaining pointing stability accurate enough to hold a laser beam steady on a dime from hundreds of miles away. Webb's coronagraph capabilities allow it to block starlight and observe much fainter objects nearby, like trying to see a firefly hovering next to a searchlight from across it. A city. This technology has revealed objects and phenomena that were completely invisible to previous telescopes, opening new windows into cosmic processes we never knew existed. The combination of these technological advances has created an instrument capable of observations that seemed impossible just decades ago. Webb can peer through cosmic dust that obscures visible light, detect the thermal glow of planets around other stars, and analyze atmospheric compositions across interstellar distances. Webb uncovered one of the most dramatic phase transitions in cosmic history, happening far earlier and more violently than anyone expected. The epoch of ionization, when the first stars and galaxies ionized the neutral hydrogen-filling space, occurred through a process so rapid and chaotic that it challenges our understanding of how energy propagates through the early universe. For roughly 400 million years after the Big Bang, the universe existed in what astronomers call the Dark Ages. During this period, space was filled with neutral hydrogen gas that absorbed virtually all light, making the cosmos completely opaque. No stars had yet formed to illuminate this cosmic fog, and any photons trying to travel through space would be quickly absorbed by the neutral hydrogen atoms. Ionization began when the first stars started shining, producing ultraviolet radiation energetic enough to strip electrons from hydrogen atoms and transform neutral gas into ionized plasma. This process should have proceeded gradually over hundreds of millions of years as stellar radiation slowly cleared the cosmic fog and made space transparent to light. But Webb discovered that ionization happened much faster and more violently than predicted. The telescope found evidence that large regions of space were completely ionized when the universe was just 400 to 500 million years old, far earlier than models suggested this cosmic transformation should have been completed. Dr. Garth Illingworth from UC Santa Cruz led studies revealing the rapid pace of ionization. "We're seeing evidence that the universe became transparent much earlier than we expected," he explained. "The process was more like ripping away a curtain than slowly lifting fog." This analogy captures how violently the cosmic transition occurred. Webb's observations reveal that ionization proceeded through the formation of massive bubbles of ionized space around early galaxies and quasars. These bubbles expanded rapidly as high-energy radiation cleared neutral hydrogen from increasingly large volumes, eventually merging to create the transparent universe we observe today. The size of these ionization bubbles shocked astronomers. Webb found bubbles stretching across 50 to 100 million light-years, far larger than simulations predicted should exist during the early phases of ionization. Creating such enormous ionized regions required radiation sources far more powerful than standard models of early star formation could provide. The telescope also discovered that ionization was highly inhomogeneous, with some regions becoming transparent while nearby areas remained opaque. This patchy ionization created a complex cosmic landscape where transparent ionized bubbles were separated by dense walls of neutral hydrogen that continued to absorb light. Webb's spectroscopic observations revealed the chemical signatures of this cosmic violence. The telescope detected emission lines from highly ionized atoms, including oxygen stripped of multiple electrons, indicating that radiation fields in the early universe were far more intense than anything that exists today. Perhaps most surprisingly, Webb found evidence that supermassive black holes played a major role in driving ionization. Ancient quasars discovered by the telescope were producing ultraviolet radiation at levels that could ionize space across hundreds of millions of light years. These cosmic lighthouses were apparently major contributors to making the universe transparent. The rapid reionization Webb observed also explains some of the telescope's other puzzling discoveries. If the universe became transparent earlier than expected, it would have enabled more efficient star formation and galaxy assembly by allowing radiation to escape more easily and reducing the thermal pressure that inhibits gravitational collapse. Webb's reionization studies revealed something disturbing about cosmic energy budgets during the universe's youth. The total amount of ionizing radiation required to clear neutral hydrogen from such large volumes so quickly exceeds what normal stellar populations should have been able to produce. Either early stars were far more luminous than modern stellar physics predicts, or additional energy sources were operating that we haven't identified. The telescope detected evidence of feedback processes where reionization itself triggered additional star formation. As ionizing radiation cleared neutral hydrogen from galactic halos, it reduced gas pressure and allowed enhanced gravitational collapse, creating positive feedback loops that accelerated both reionization and galaxy formation. These discoveries reveal that reionization wasn't just a passive clearing of cosmic fog. It was an active, violent process that fundamentally altered the conditions for cosmic structure formation. The universe didn't gradually wake up from the dark ages. It experienced a sudden, violent transformation that permanently changed how matter and energy interact on cosmic scales. Webb discovered a cosmic mystery that challenges our understanding of galaxy evolution. Entire populations of galaxies that should exist in the early universe are simply missing. The telescope's deep surveys revealed massive gaps in the galactic fossil record, suggesting that cosmic violence or unknown physics destroyed or prevented the formation of countless stellar systems during the universe's youth. The missing galaxy problem emerges from comparing Webb's observations with theoretical predictions about early cosmic structure formation. Computer simulations of cosmic evolution predict specific numbers and types of galaxies that should exist at different epochs in universal history. These models account for dark matter clustering, gas dynamics, star formation processes, and feedback mechanisms to forecast the galactic populations we should observe. But when astronomers tallied the galaxies Webb actually found in the early universe, the numbers didn't match predictions. Entire categories of expected galactic systems were either completely absent or severely underrepresented in the cosmic census. The universe appears to be missing billions of galaxies that should have formed during its first billion years. Dr. Stephen Finkelstein from the University of Texas led surveys that revealed this cosmic deficit. We're seeing far fewer small galaxies in the early universe than our models predict, he explained. Either these galaxies never formed or something destroyed them after they assembled. Both possibilities have disturbing implications for cosmic evolution. The missing galaxies aren't random. They follow specific patterns that provide clues about what might have caused their absence. Webb found that low-mass galaxies are particularly underrepresented in the early universe, while massive systems appear in roughly expected numbers. This mass-dependent deficit suggests that small galaxies were more vulnerable to destruction or suppression than their larger counterparts. One possibility involves feedback processes from early star formation that were far more violent than modern phenomena. When the universe's first massive stars died in hypernova explosions, they might have released so much energy that they completely disrupted nearby small galaxies, scattering their material across intergalactic space before stellar systems could fully assemble. Webb's observations also suggest that supermassive black holes might have played a role in galaxy destruction. The telescope found evidence of powerful quasar activity throughout the early universe that could have ionized and heated gas across vast regions, preventing small galaxies from forming or stripping away their material after assembly. Another theory involves dark matter interactions that were different during the universe's youth. If dark matter particles underwent annihilation or decay processes that released energy, these events could have heated gas and disrupted galaxy formation on scales much larger than normal stellar feedback could affect. The missing galaxy problem also appears connected to cosmic reionization. Webb's observations suggest that the violent process of making the universe transparent might have been energetic enough to destroy small galactic systems entirely. The intense radiation fields that ionized cosmic hydrogen might have simultaneously evaporated the gas reservoirs that small galaxies needed to continue forming stars. Perhaps most disturbing is the possibility that the missing galaxies reveal fundamental flaws in our understanding of cosmic structure formation. If our models consistently overpredict galaxy numbers in the early universe, it might indicate that we misunderstand basic processes like dark matter clustering, gas cooling, or stellar feedback mechanisms. Webb also discovered fossil evidence of destroyed galaxies in the form of isolated stellar streams and orphaned star clusters scattered throughout intergalactic space. These stellar refugees represent the remnants of galactic systems that were torn apart by unknown processes, leaving behind only faint traces of their former existence. The telescope's spectroscopic observations revealed unusual chemical compositions in early intergalactic gas that suggests substantial material was ejected from galaxies through violent processes. This metal enrichment of cosmic voids indicates that galaxy destruction was widespread enough to contaminate large regions of space with processed stellar material. Some researchers propose that the missing galaxies might be hidden rather than destroyed. These systems could have formed but remained dark, containing little or no star formation that would make them visible to telescopes. If massive populations of dark galaxies exist throughout the early universe, it would completely alter our understanding of cosmic structure. The missing galaxy problem forces astronomers to confront the possibility that cosmic evolution was far more violent and destructive than previously imagined. Rather than the gradual assembly of structure through gravitational collapse, the early universe might have experienced widespread galactic catastrophes that permanently altered the cosmic landscape. Webb's discoveries paint a picture of cosmic infancy that's radically different from the peaceful, gradual development astronomers once envisioned. The early universe was a realm of extraordinary violence where hypernovas exploded with unprecedented fury. Supermassive black holes devoured matter at impossible rates, and galactic collisions reshaped cosmic structure through catastrophic mergers that have no modern equivalent. The evidence for this cosmic violence appears throughout Webb's observations. The telescope found chemical signatures indicating that stellar explosions in the early universe released energies far exceeding anything observed today. These ancient supernovas weren't just larger versions of modern stellar deaths. They were fundamentally different phenomena operating under conditions that no longer exist. Hypernova explosions from the universe's first generation of stars apparently released enough energy to ionize space across hundreds of millions of light years, simultaneously creating heavy elements and triggering shock waves that stimulated rapid star formation throughout galactic neighborhoods. These cosmic catastrophes were so energetic they could alter the evolution of entire cosmic regions. Webb also revealed evidence of galactic cannibalism operating at unprecedented scales during the universe's youth. The telescope detected massive galaxies that appear to have consumed dozens of smaller companions, growing to enormous sizes through violent mergers that would completely disrupt galactic structure in today's cosmos. Dr. Mauro Giavalisco from the University of Massachusetts led studies documenting this early cosmic violence. The early universe was a much more dynamic and chaotic place than we realized, he explained. Processes that are rare today were commonplace during cosmic infancy, creating conditions that enabled rapid evolution through violent means. The violence extended to black hole formation itself. Webb found evidence that some supermassive black holes formed through direct gravitational collapse of enormous gas regions, catastrophic events that would instantly create monsters containing millions of solar masses without any stellar progenitor. These direct collapse events represent cosmic violence on scales that dwarf any phenomena in the modern universe. Galaxy cluster formation also proceeded through extraordinary violence during the universe's youth. Webb detected evidence of cluster mergers involving dozens of massive galaxies simultaneously, creating collision energies comparable to billions of supernova explosions. These cosmic crashes heated intergalactic gas to temperatures exceeding 100 million degrees and generated shockwaves that propagated across vast cosmic distances. The telescope's observations suggest that violent feedback processes were essential for shaping cosmic evolution. Rather than hindering structure formation, the extreme energy releases from early stars, black holes, and galactic collisions appear to have accelerated development by triggering rapid gas flows, enhanced cooling mechanisms, and efficient matter redistribution. Webb found that even star formation itself was more violent during cosmic youth. early stellar nurseries show evidence of formation rates exceeding 1,000 solar masses per year, compared to our Milky Way's current rate of about 2 solar masses annually. This frenzied stellar birth was apparently sustained through violent processes that compressed gas clouds and triggered massive star formation episodes. The cosmic web's rapid development also required violent processes. Webb detected evidence of dark matter interactions that were far more energetic during the universe's youth, possibly including particle annihilation events that released tremendous energies while simultaneously accelerating structure formation through enhanced gravitational clustering. Perhaps most significantly, Webb revealed that this cosmic violence was self-regulating. The violent processes that accelerated early evolution also created conditions that eventually moderated further violence. As the universe expanded and cooled, the extreme densities and energies that enabled such catastrophic events gradually diminished. The transition from violent youth to relative cosmic maturity appears to have occurred around 2 to 3 billion years after the Big Bang. After this epoch, galactic mergers became less energetic, stellar formation rates decreased, and supermassive black holes entered more stable feeding phases that characterize the modern universe. Understanding this violent cosmic youth is crucial for comprehending how the universe evolved from primordial simplicity to today's complex structure. Webb's discoveries suggest that extreme violence wasn't a destructive force that hindered cosmic development. It was the engine that drove rapid evolution and enabled the universe to achieve complexity far faster than gradual processes alone could have accomplished. Webb's discoveries don't just challenge individual theories about cosmic evolution, they force a fundamental reconsideration of how the universe works at the most basic level. The telescope has revealed that nearly every assumption astronomers made about cosmic development, from galaxy formation to black hole growth to the expansion of space itself, requires dramatic revision. The implications begin with cosmology's most fundamental models. The standard lambda CDM model, which describes cosmic evolution through the interplay of dark matter, dark energy, and normal matter, successfully explained most observations for decades, but Webb's discoveries reveal phenomena that this model cannot accommodate without major modifications or additional physics. The rapid formation of massive galaxies, the early appearance of supermassive black holes, and the accelerated timeline of cosmic structure formation all suggest that the early universe operated under conditions far more extreme than standard cosmology predicts. Either our understanding of dark matter and dark energy is incomplete, or unknown forces shaped cosmic evolution during the universe's youth. These discoveries also affect our understanding of cosmic habitability and the potential for life elsewhere in the universe. If heavy elements became available much earlier than expected through rapid stellar evolution, and if complex galactic structures formed quickly enough to create stable environments, then conditions suitable for life might have emerged billions of years sooner than previously thought. Dr. John Mather, Webb's senior project scientist and Nobel laureate, captured the magnitude of these implications. We're seeing the universe do things we didn't think were possible. Every major discovery is forcing us to reconsider basic assumptions about cosmic evolution. The accumulated weight of Webb's observations suggests that our cosmic worldview requires fundamental revision. The telescope's discoveries also have profound implications for understanding the nature of time and causality in cosmic evolution. If the universe achieved complex organization far more rapidly than models predict, it suggests that cosmic development isn't limited by the gradual processes we observe today. The early cosmos might have operated according to accelerated physics that enabled rapid transitions between fundamentally different states. Perhaps most significantly, Webb's observations challenge the assumption that cosmic evolution proceeds through gradual, incremental changes. Instead, the telescope reveals a universe that undergoes rapid transitions, violent reorganizations, and sudden phase changes that can transform cosmic structure on timescales much shorter than traditional models allow. The Hubble tension crisis exemplifies how Webb's precision has revealed fundamental problems with our understanding of cosmic expansion. The fact that we cannot measure one of the universe's most basic properties, its expansion rate, despite decades of increasingly sophisticated observations, suggests that unknown physics operates on the largest scales. These measurement contradictions might indicate that space itself behaves differently than general relativity predicts under extreme conditions, or that cosmic expansion involves mechanisms we haven't identified. The universe Webb reveals operates according to rules we're only beginning to glimpse. The telescope's discoveries also force reconsideration of cosmic uniqueness and the anthropic principle. If the early universe was capable of such rapid and dramatic evolution, it suggests that cosmic development might be far more dynamic and variable than we assumed. Different regions of space might have evolved along completely different pathways, creating cosmic diversity that extends far beyond what we observe in our local cosmic neighborhood. Webb's revelations about early cosmic violence and rapid structure formation also affect our understanding of cosmic fine-tuning. Rather than requiring delicate balances of physical constants to enable structure formation, the universe might be robust enough to achieve complexity through multiple different evolutionary pathways, many of which involve far more extreme conditions than we previously considered possible. For astrobiology, Webb's discoveries suggest that life might have had far more opportunities to emerge throughout cosmic history than we realized. If complex chemistry became available billions of years earlier than expected, and if stable galactic environments formed rapidly, then the universe might have been suitable for life across much longer timescales than traditional models predict. These discoveries represent more than just updates to astronomical knowledge. They reveal that the universe is fundamentally more mysterious, more dynamic, and more capable of surprise than we ever imagined. Webb has shown us that cosmic evolution operates through mechanisms we're only beginning to understand, following rules that push the boundaries of known physics. When the James Webb Space Telescope first turned its golden mirrors toward the deepest reaches of space, astronomers expected to find a young, simple universe slowly awakening from the cosmic dark ages. Instead, they discovered a cosmos that had already achieved extraordinary complexity and organization when it was supposedly still learning the basic rules of physics, the universe. Webb revealed challenges every comfortable assumption we held about cosmic evolution. Massive galaxies blazing with the light of billions of stars existed when the cosmos was barely 3% of its current age. Supermassive black holes were already feeding voraciously when there hadn't been enough time for them to grow through normal processes. The cosmic web of large-scale structure was already well developed when it should have been in its most primitive stages. These discoveries represent more than just surprising observations. They reveal that the early universe operated under conditions so extreme that familiar physics was pushed beyond its normal limits. The cosmos achieved in a few 100 million years what our models said should take several billion, through processes so violent and rapid that they have no equivalent in today's universe. The implications ripple through every aspect of our understanding. If the universe could organize itself so quickly and dramatically during its youth, it suggests that cosmic evolution isn't limited by the gradual processes we observe today. The early cosmos was a realm where hypernova explosions ionized space across hundreds of millions of light years, where galaxies merged and cannibalized each other with unprecedented violence, and where supermassive black holes formed through direct gravitational collapse. Webb has shown us that the universe's capacity for surprise and complexity far exceeds our theoretical predictions. The telescope detected mysterious red dots that don't fit any known category of cosmic object, found evidence of cosmic reionization proceeding far more rapidly than expected, and revealed that entire populations of predicted galaxies are simply missing from the cosmic census. Perhaps most fundamentally, Webb's discoveries suggest that our understanding of cosmic expansion itself is incomplete. The Hubble tension crisis reveals that we cannot measure one of the universe's most basic properties despite decades of increasingly precise observations indicating that unknown physics operates on the largest scales imaginable. The universe Webb revealed is stranger, more violent, and more dynamic than we ever dared imagine. But it's also more remarkable. The cosmos demonstrated an extraordinary capacity for rapid evolution and complex organization during its youth, achieving in cosmic moments what seemed to require cosmic ages. These discoveries transform our perspective on humanity's place in the cosmic story. If the universe was capable of such rapid chemical evolution and complex structure formation during its youth, then conditions suitable for life might have emerged billions of years earlier than we thought possible. The cosmos might have been a suitable stage for biological evolution across far longer timescales than traditional models predicted. Webb's revelations also suggest that cosmic evolution operates through mechanisms we're only beginning to understand. The telescope has pushed back the frontiers of observation to epochs when the universe was fundamentally different from today, revealing processes that operated under conditions so extreme they have no modern analogs. Looking forward, Webb's discoveries point toward even more profound questions about the nature of cosmic evolution and the physical laws that govern it. If the early universe could violate so many of our theoretical expectations, what other surprises await as we peer even deeper into cosmic history? The telescope represents humanity's most ambitious attempt to understand our cosmic origins, and its discoveries have revealed that those origins are far more complex and mysterious than we ever imagined. Webb has shown us that the universe is not just vast and ancient. It's fundamentally more dynamic and capable of rapid transformation than our models predicted. We stand at the threshold of a new era in cosmology, armed with an instrument capable of observing the universe's most distant and ancient phenomena. Webb has already revolutionized our understanding of cosmic evolution, but its most profound discoveries may still lie ahead as it continues to probe the deepest mysteries of space and time. The universe James Webb has revealed is not the cosmos we expected to find, but it might be exactly the universe we needed to discover. One that challenges our assumptions, expands our understanding, and reminds us that reality is far more extraordinary than our theories dare predict.